This video introduces the Kolmogorov-Smirnov Test in statistics. The test is named for the two Russian mathematicians who developed it, Kolmogorov and Smirnov. No, not that Smirnov, this Smirnov. The KS test could be used to test whether data follow any particular pre-specified distribution, or there's a variant of the test which allows us to see whether two sets of data come from the same underlying distribution. But what we'll be doing in this video is focusing on using the KS test as a test for normality. Some background is in order before we get started. Remember how a hypothesis test works. We've got some data and we've got a null hypothesis. And we want to see whether the data are consistent with that null hypothesis. To that end, we compute some measure of distance between the data and the null, the observed and the expected. And then we want to see how big that difference is as compared to some sort of reference distribution. And so most commonly in bell curve based tests, we'll compute that distance as observed minus expected over standard deviation and compare this with a z or a t distribution as our reference distribution. In a KS test, we'll still look at this sort of thing, a distance between observed and expected, only now we're looking at the distance between observed and expected CDFs of the data. Let's take a simple example. Let's suppose we've got 10 data points, and we wish to test whether these 10 data points come from a normal population. Notice, by the way, that those data have a sample mean of 50 and a sample standard deviation of 20. So let's begin by looking at the observed CDF, cumulative distribution function of the data. In other words, the empirical CDF, to use KS test jargon terms. For each data value, we need to compute the CDF, the percentage of data equal to or less than that data value. And so, for example, our first data point is 22. We have 1 out of 10 data points which are 22 or fewer, and so a CDF of 1 out of 10 or 0.10. But for a number just slightly less than that, say 21.99, none of the data are 21.99 or less, and so that CDF is 0 out of 10 or 0.00. Let's draw a picture. Here's our picture. Our first data point was 22. So from 21.99999 on down, there's none of the data there. We hit 22, 1 data point out of the 10, up through 23, 24, 25, 26, 27. And when we hit 28, now we've got 20% of the data, up through 32, and so on. This is our empirical cumulative distribution function. This is what we observed from the data. We can also work out, remember we're comparing observed and expected, we can also work out the expected CDF, or the theoretical CDF in KS test jargon terms. For each point in the data range, we need to compute the percentage of data that we would expect if the data really are from a normal distribution. Our first data value was 22, mean of 50, standard deviation of 20, and so we can either compute the z-score of negative 1.40 and 0.081, 8.1% of the data are 1.4 standard deviations or more below the middle, or we can simply compute the norm.dist function. Either way, we're finding 8.1% of the data should be 22 or less. Here's our picture for our theoretical CDF doing these computations for all the data. 22 or fewer, we should have 0.081 of the data. 25 or fewer, 28 or fewer, 30 or fewer. Notice the mean is 50, so for 50 or fewer, we should have half the data, and so on. Virtually all the data will be 120 or fewer. Question. Is our empirical CDF, our observed values for the data, close to our theoretical, our expected CDF? Is this close to this? How do we measure the distance between those two? That's an excellent question. I'm glad you asked it. Our test statistic, the KS test, is defined as the largest distance in absolute value terms between those two lines. The biggest absolute value distance between the red and the blue. Largest absolute distance. And notice something. While in theory, that gap could be anywhere along here, but in practice, it's going to happen at one of the jumps. It's not going to be here because the distance here is bigger. It's not going to be here because distances at the endpoints will be bigger. And so all we need to look at is the places where we've got a data point, where the CDF, the empirical CDF, jumps in value. Let's do the computations. Here's a table. These were our data values. I've got the empirical CDF, and it jumps from here to here. It jumps from here to here. It jumps from here to here. The theoretical CDF. And then we compute the distance between these points and the theoretical. That absolute distance is here. Let's work through an example. And in particular, we'll focus on the second data point, the number 28. At 28, the empirical CDF jumps from 0.1 to 0.2. 1 out of the 10 data are strictly less than 28, but 2 out of the 10 data are 28 or fewer. The theoretical CDF is 0.136. We either compute a z-score or we use the norm.dist function. But either way, it's telling us if things are truly normal, with mean of 50 and standard deviation of 20, we should expect 13.6% of the data to be 28 or fewer. How far is the bottom distance, the 0.1 from 0.136? It's 0.1 minus 0.036, absolute value terms, 0.036 away. And similarly from 0.2 to 0.136, that distance in absolute value terms is 0.064. And so we do this, visually we're looking at these distances from here to here, from here to here, between the red and the blue. And we do that for all of our data. The Kolmogorov-Smirnov Test statistic is the largest of those distances. And so here are all of our distances. Got a really tough question for you now. Brace yourselves. What's the biggest number there? The biggest distance is 0.258. That's our KS test statistic. Question then. Is that value of 0.258 big or small? Is it a big test statistic, meaning there's a big distance between the data and what we expected? And if there's a big distance between data and expected, we would reject the null hypothesis. Or is that 0.258 a small distance? The data were pretty close to what was expected, which means that we don't reject the null hypothesis. Big distance or small distance? And of course the answer is it depends. Compared to what? Compared to our reference distribution of how KS test statistics behave. Now, Kolmogorov and Smirnov worked out the sampling distribution of their statistic for the situation where the mean and standard deviation were known. In other words, they're testing here the hypothesis that the population is normal with a mean of 50 and a standard deviation, population standard deviation of 20. But in practice, we're going to estimate that mean and standard deviation from the data. This means that the null hypothesis we're really testing is simply that the population is normal. This affects the critical values of the test. A chap by the name of Hubert Lillefors worked out these critical values, and two other chaps by the name of Mason and Bell later revised and improved Lillefors' values. And a table of these values is shown here. And I've given the references, but let's see what this table means. Let's suppose we've got 12 data values. For 12 data values, a KS statistic of 0.243 would have a p-value of exactly 0.05. Anything bigger than that, the p-value will be smaller than 0.05, and we would reject the null hypothesis. Any test statistic smaller than 0.243, we're in non-reject world, assuming the traditional 0.05 significance level. For our example, we had 10 data points, and our test statistic was 0.258. For 10 data points, 0.258 falls somewhere between those. Our p-value is somewhere between 5% and 10%. And so if you're an ardent rabid traditionalist, you do not quite reject the null hypothesis that our data come from a normal distribution. So in summary, the Kolmogorov-Smirnov test is a well-known test and a powerful test to see whether data are from a normal distribution or any specified distribution. The test statistic is the maximum distance between the observed and expected, the empirical and theoretical CDFs of the data. It's a little bit cumbersome to compute, but it's a fairly straightforward concept and leads us to a very well-known test for distributions.